Number 25 is on carbohydrates, which is from the new material that you're learning for the final. Now, it's a roadmap, and these are usually a little complicated. Now, what does this question ask, first of all? This question says, determine and draw the Fisher projection of monosaccharide A. So we're looking to figure out what A looks like. Based on the following information. Both reduction with NADH4 of A and reduction with NADH4 of C give the same structure B. Kilani-Fisher synthesis of C gives you D-glucose and D-mannose in equal proportion. So now we have to figure out what is the structure of A. So to solve this problem, we're going to start with the structures they gave us, because that's probably the best place to start. So we are told whatever C was underwent the Kilani-Fisher synthesis and made both D-glucose and D-mannose. Now, what the Kilani-Fisher synthesis does is it takes a carbohydrate. Let's say I have a 3-carbon chain, or a short carbohydrate like this. And I'll just put all the OHs on the right side. What the Kilani-Fisher synthesis does is it extends the carbon chain by 1, meaning this CHO, let's actually number these. Let's say this is 1, 2, 3, 4, 5. What the Kilani-Fisher synthesis does is it basically sticks a whole other carbon onto carbon 1, and that carbon 1 now becomes one of these, the ones where there's one OH and one hydrogen. But the rule about this is that whatever that carbon 1 becomes, that OH, when that carbon 1 becomes the single bond with the OH, that OH can be on the right or the left. Because originally it was a CHO group, a carbon that is flat. And that OH, when that double bond O becomes an OH, it can either be pointing to the right or the left. So you have two possible products. The one I just drew here, and then the other possible product where that OH is on the right. So we can translate that idea to this now. If the Kilani-Fisher synthesis reaction going forward adds a carbon, going backwards we're chopping a carbon off. Which means when I go backwards, I'm erasing this CHO and I'm erasing this CHO, and now the carbon with the OH on top becomes my new CHO. So this here, this is one possible structure for C, and now I erase this, and now this becomes my CHO, and this is my other possible structure of C. Oh wait, they're the same structure, because C, when it undergoes the Kilani-Fisher synthesis and this gets an extra carbon added to it and this becomes an OH, a carbon OH, that OH could have been on the right or that OH could have been on the left, and that's why it's D-glucose versus D-mannose. So we know what the structure of C must be. It must be this. So we know the structure of C. CHO. With an OH on the left, an OH on the right, and an OH on the right. Love this kind of question. Okay, so we know what C is, and now what would C look like if you took that and reacted it with NADH4? Well, remember what NADH4 does. It's a reducing agent, and it turns your CHO group into a CH2OH. So structure B, after you treat this with NADH4, would look like CH2OH on top, and now all the other OHs are still the same, because none of those get affected. So I have an OH on the left, an OH on the right, and an OH on the right. Now here's the weird thing. They tell us that structure A will give us this exact same structure. But because A is a different letter from C, that means they're different structures. I can't draw the same thing for A. So what could structure A look like if after being treated with NADH4 I get this? And now this is the trick. This is a trick you always have to be aware of. If you were to take this structure and kind of rotate it around in a circle, I rotate it around, and so now this is on top and this is on bottom. When I rotate it that way, these OHs will end up on the left. And if I were to draw that out, what it would look like is CH2OH. And now those two OHs that were on the bottom are on the left on the top, and that OH is on the right there. So I'll number these so it's a bit easier to keep track if you can't visualize the rotation. So let's say this is 1, 2, 3, 4, 5. If I spin this like that, then this is carbon 5, 4, 3, 2, and 1. And then the hydrogens just get filled in. And now, if I work based off of this, what would this have been before the NADH4 reaction? This would have been a CHO group. And now this structure is different from this structure here, but through this clever idea of rotation, you end up getting the same thing after treating it with NADH4. Even though these look different, once you make that bookend exactly the same, those both being CH2OHs, you can rotate it and you'll end up getting the same thing. Because all I have to do is make this a CH2OH again and flip it around that way, and now all the OHs would match up. And so that was the trick of this question, but for our answer, this is our structure for A, where you have 2 OHs on the left, 1 OH on the bottom right, and then your standard aldose structures beyond that. But that's how you got to the answer for number 25.